I will start the course of Hodge theory. So first of all, some references for the course. Is the sound okay? It's fine? Okay. Okay, so our main reference is Voisin's book. Claire Voisin, Hodge theory. And complex algebraic geometry. Volumes 1 and 2. Our second reference, it's also one of the main references for this course, are Hossein's books in Hodge theory, Hossein Mobasati. A course in Hodge theory. Volumes 1 and 2. I think the volume 1, it's called With a View. Volume 1, With a View towards multiple integrals. And the volume 2 is periods of algebraic cycles. Okay, beside that, well, these books can be found in the following website. And beside that, I plan to give a proof of Serre's Gaga correspondence. So I should add here Jean-Pierre Serre, geometry, algebraic, and geometry analytic. Well, these are the main references. Beside that, I will also pick up some parts of other books. Whenever we get there, if you need some references, you ask me, and I can give you more reference. Okay. Before starting, I want to say that this course is not planned to have exams. I am just planning to give lists to grade the notes, and I will travel 3 weeks from. So I will be traveling from September 2 to 20. So I will try to look someone to replace me in these classes. Well, we will see what we will do. Maybe I will give a long list. I don't know. Okay. So what is Hodge theory about? Well, Hodge theory can be regarded as an study of the topology of complex manifolds, right? Complex projective manifolds. well, it began from the studies of the algebraic topology of algebraic varieties, started by Lefschetz, and then it evolved with Hodge theory about harmonic integrals, and he was trying to develop a theory in such a way to recover all results obtained by Lefschetz, but in an analytic way. So before starting, I need to recall some background of algebraic topology that we will use along the course. Okay, so today's class is just recalling some basic facts about singular homology and cohomology. Okay, so first of all, definition. So let X be a infinity smooth manifold and consider the standard simplex delta n is just the set of points in Rn plus 1 such that they are positive and their sum add up to 1. Okay, so this is the standard simplex in Rn plus 1. So this is a singular n simplex on X is a function, a differential function f from delta n to X. Okay, so the group, the free abelian group, generated by them, generated by all the n singular n simplex, is denoted like this: Cn of X, and it's exactly the same thing as the set of formal sums Ni Fi I in a set I, such that Ni are integers, Fi are singular n simplexes, and I is finite. Okay, so this is an abelian group, and we define an operation, a boundary operation, on any singular n simplex. The following way. So delta n of f is defined to be the sum I equals 0 to n minus I to the I, f composed with I. Well, this is a bad letter, maybe ik. Okay, where ik is the map defined from delta n minus 1 to delta n, that is sending x0 to x n minus 1 to the vector x0 to xk minus 1, 0, xk, and xn minus 1. You just add a 0 in the case position. Okay, this boundary operator can be extended. We can extend it by linearity to an operator on the whole, not just in one simplex, but in the whole group of singular simplexes. So we have a map here that goes from Cnx to Cn minus 1x. And this is called the boundary operator also. Okay, so it's an easy exercise. It is an exercise to check that this boundary operator, well, let's denote it delta n, satisfies the following relation, right? So this means that, in other words, this sequence is a complex. Of abelian groups. Okay, what does that mean? This means that if we denote set n of x as the kernel of delta n of the boundary operator, this is called the group of n cycles, and we denote, well, let's continue here. And if we denote Bn of x, the image of delta n plus 1, the set of the group of n boundaries, then every boundary is a cycle. Okay? And so we can define a cohomology. So this a homology. Define the n homology groups of x in the following way. Hn of x is by definition the homology of the complex of singular chains on X with the boundary operator. So this is the same as Cn of X over Bn of X. Okay? I'm just recalling these facts. I'm assuming that you have already some knowledge about this. So, what's next? So, well, this singular homology groups, they are functorial in the following sense. So, remark, given any smooth map, f from X to Y, this map induce we have in natural homomorphisms induced by this map in singular homology. These are and these maps satisfies furthermore given any two maps X F from X to Y and G from Y to C, we have that the composition, the induced map of the composition is the composition of the induced maps, right? This is what it means to be functorial. And also, obviously, the identity will map to the identity. Sorry. Okay, so in particular, these homology groups, Hn of X, are C-infinity invariants. This means that they are invariant under diffeomorphisms. Furthermore, we can show, it can be shown, it's not so hard, that they are in fact homotopy invariants. And this follows from the fact that if we have two maps from between smooth manifolds, which are homotopic, then the induced maps are the same. Okay, I won't prove these things. I am assuming that you already know about it. I'm just recalling these facts. Okay, any questions? Okay, so maybe I should draw some pictures. I don't know, maybe first I will recall another definition. Okay, definition. Beside this singular homology group, we have a relative version of the singular homology. So if we consider a pair xi a of smooth manifolds such that A is contained in X, then I have two complexes, right? I have the complex of singular chains on X, right? And we have the complex of singular chains on A, right? And the inclusion induce an inclusion here. I mean, every n plus 1 simplex in A will be an n plus 1 simplex in X just by the inclusion, right? So we have an inclusion of abelian groups, and with this inclusion of complexes, we can define a quotient complex right, induced by the same boundary operators as before. Okay, so from here, we define, using this complex, we define the relative homology groups. We define the relative homology the following way: Hn of the pair Xa is by definition the homology of this complex. Okay? So it is just the kernel of this map over the image of this map. Right? Since these are complexes, this is also complex. Okay? Good. And why do we do this? We do this since we want to, well, these relative homology groups are useful because of the following observation. You can notice that we have a short exact sequence of complexes of abelian groups. Right? And it's just considering the inclusion of this complex inside the complex of singular chains on X and just taking the quotient. Right? And whenever we have a short exact sequence of complexes of abelian groups, we have this zigzag lemma that provides us with a long exact sequence in homology or cohomology, depending on the case, right? So using the zigzag lemma, we obtain a long exact sequence in homology. Right, this is just Hn of A. This is the inclusion, Hn of x. Again, the inclusion, Hn of x relative to A. And the boundary operator, boundary map, Hn minus 1A. This is exact. Okay, any questions? No complaints? No? Okay, maybe I should draw some pictures. No, pictures. Okay, so what is this relative homology means? I mean, when it is an element, let's say beta of, I don't know, hk x relative to A. So if we draw something, I don't know, I'm not good at pictures. So let's do something like this, x. So here we have a subspace, let's say something like this, A. A. And an element will be, it's not a cycle. I mean, it's something that can have boundary, but its boundary must lie inside A. Okay, so it can be something like this. So something like, I don't know, something like this. This can be beta, and the boundary of beta will be something lying inside A. Okay, and if A is empty, so if A is empty, then this thing is exactly the same thing as the normal singular homology groups, right? So here I'm saying that the boundary of B is empty. It has no boundary. Okay. What? Wait, where is it? Bigger. But is this size good? Really? Okay. Sorry. Okay. Okay, so well, let me recall a relationship between the fundamental group and the first homology group. So we will be interested in computing these homology groups, but for algebraic varieties. So even if you have not taken a course in these topics, you can use this like a black box and know how to use the theorems and do the computations. We need to do the computations. Okay, so proposition first part is this size okay? Okay, so the first part is let X be path connected topological space and path connected topological space. Then the first homology group is isomorphic to the abelianization of the fundamental group. So for some x0 in X. So, and this is exactly the same thing as the fundamental group divided by the subgroups generated by the commutators. This is the derived group. Okay? So this is one property. And another property is that let X tilde be a connected, simply connected topological space and let G be a group acting over X tilde in such a way that the action is properly discontinuous. So in such way that the action is properly discontinuous. Okay, so what does this mean? This means that we can cover X tilde by open sets U such that if G1 acting on U intersects G2 acting on U, then G1 is G2. Okay, so we can find a covering of X tilde by open sets such that whenever we act over these open sets, they never intersect each other. Okay. So under this hypothesis, the quotient of the action has fundamental group isomorphic to G. Okay, so these are standard facts that we are recalling from an algebraic topology course, and we're just using these facts. So okay, so now I want to give you some examples of how to compute certain homology groups or of certain algebraic varieties. These are the most simple examples that I could imagine. And the purpose of the first part of the course is to develop more machineries to compute these homology groups for certain kinds of algebraic varieties that are the projective varieties, and we will do that following Lefschetz approach. Okay, so examples. Okay, so do you have any questions so far? Really? Okay. So first example, example 1, consider so
you don't need a hypothesis on the group.
sorry?
You don't need a hypothesis on the group in the second property. Just
Yeah.
any group active.
Yes. So consider the following algebraic curve. So let X be the set of points x, y in C2 such that y to the square is equal to f of x, where f of x is equal to x minus r1 to x minus rd is a polynomial with complex coefficients, and all its roots are simple. Okay? We assume that. Okay, so we want to see the face of this guy. We want to see what is this topologically. This is a curve in the plane, in the complex plane C2, and so it has a real dimension too. It is a surface, a real surface. So if you want to see which surface is this, we need to observe the following thing. So notice, so know that for every point x in C different from the roots, I have exactly two values on y that lie in x, right? There exists exactly y and minus y in C such that xy and x minus y belongs to x, right? In particular, I have that this projection map, the first projection, if I remove the roots of the polynomial, so it is, here I have to remove R1, 0, RD0. So this map is a covering map, right? So it is a covering map with two decks. Decks is the word in English? I'm not sure. With two sheets. Okay, so I want to see this guy. My strategy to see the face of this guy is to produce sections of this map. I will try to produce sections of this covering in such a way that I can cover all x with a finite set of sections. In fact, I will do it with just 2 sections. Okay. So how do I do that? So let's fix some point x0 in C minus R1 to RD. And I want to define a section. I'm looking for some map, define it in some open set, right? Some open neighborhood of x0. Right? 2x S such that it is a section of this map. That means that S of x is equal to x and y of x such that y of x squared is equal to f of x for every x in U. Right? Okay, so, and what does this mean? This means that I am looking for a branch. I'm looking for a branch of the square root of f, right? A complex branch of this. Okay. So how do we construct a branch of the square root of f? It's not so complicated. So our first candidate is just to, like the innocent, like the naive candidate is just to take the exponential, right, of 1 over 2 of the log of f of x, right? This will be like the naive candidate, y of x. But this doesn't make any sense, right? So what we do is to take what it should be, the definition of the log, and we can define it in terms of integrals. It's like applying the fundamental theorem of calculus, right? You just fix a point, you integrate until another point, and you take the integral of the derivative of the log of f, right? It's just f prime of z over f of z, this set, right? So this is a well-defined meromorphic form. But, this integration is not well-defined because we are not fixing any path to integrate between x0 and x, right? So we are here. Let's draw here. We're in C minus R1 to RD, right? So we have here some roots. I don't know, R1, R2, R3, R4, R5, R6. And we fixed one point here, x0, and we take any other point x here, and we are trying to integrate along some path. But this is not well defined because we could have different values if we integrate along a different path. So if we, for instance, if we go through a path like this, the value will change by the residue that the meromorphic differential form leaves in this root, right? So what is the residue? So since the roots of f are simple roots, I know what is the residue of this differential form, right? The residue of f of z, this set over f of z, f prime, on any root, it will be exactly f prime of the root divided by, well, I'm not looking for the residue of this, I'm looking for the residue of this, right? This divided by 2 f prime of Ri, and this is 1/2. Okay? So this integration is defined up to some so this is defined up to addition of something here, right? Of 1/2 times 2 pi I the integers, right? So this is defined up to an addition of an integer multiple of pi I. But the exponential of this thing will give you plus or minus 1, depending on if this integer multiple is odd or even, right? So in particular, this y of x is defined up to multiplication of plus minus 1. So what should I do in order to assure that I don't have this ambiguity of this map? So what I would like to do is that restrict, if I want to restrict the domain of this integration in such a way that every time that I give a loop around any root, I assure that I'm giving a root around 2 roots at the same time. If I do that, I am assuring that the residues always gives you an integer, and so you are adding multiples of 2 pi I. And so when you take the exponential of this, this will be well defined, right? So what we have to do is to take an open set in the following way. So we have to construct paths joining the pairs of roots, right? So here we can pair them in this way, and we remove these paths, right? So we consider U, we define U to be C minus a set of paths, let's say gamma 1 until gamma, I don't know, gamma k, right? Such that each gamma I is joining 2 different roots, and they are disjoint, right? Okay, but I can do this if the number of roots is an even number, right? But if it's not an even number, what should I do? So suppose we have another root here. Okay. Every time that I go around this root, I will have an ambiguity. So the only possibility that I have is to remove this thing, I mean to restrict U in such a way that I never go around this guy. And how do you do that? You just need to construct a path connecting this guy with the infinity. Right? If you think that you're not anymore in the complex plane, but you are in the Riemann sphere, you're adding the infinity. Right? So depending on, so let's say, here. So depending on if D is even, I can take just K equal to D over 2 paths connecting each pair of roots in any way. You can pick the way that you like. And if it's odd, you take, I don't know, you take D minus 1 over 2 paths connecting roots, pairs of roots, and one extra path that it will be the gamma D plus 1 over 2 connecting the missing root with infinity here in the extended complex plane. Okay? So in this way, we have this y function, and we're in the ground to see how is x, how does x looks like. So I will draw this picture. Okay, so we have one copy here of the extended plane, right? So let us do the draw in the case D is even. Okay, so D even, we have the infinity here somewhere, and we have this even number of roots, right? And I have this path connecting them. So I remove this path. I can open them a little bit to make a hole here, right? So I can assume that this is something like a hole in the sphere. And I have, I don't know, R1, R2, R3, R4, R5, and R6. And I have this map x, y of x that goes to my variety x, right? So, and on the other side, I have the same domain. I have here a copy of infinity. I have here the other copies of, I don't know. Let's do it in this way. So I have this other copy. R1, R2, R3, R4, R5, and R6. And I have this other function, x minus y of x, right? This other branch. And what I know is that whenever I am walking around here in this sphere, I mean, let's say that I'm here and I fixed a point x0 and I start walking here, and whenever I get through this this hole, and I pass through it, the value that I have here, I have a discontinuity of the value of this function. When I compose this path with this map, this function is discontinuous when I pass through any hole. And how will it change? It will change just by a sign, because the only possibilities of this image are two values. The other value is minus the value that it should be. So whenever I pass through this hole, I will appear in this other side. If I want to do it continuously, the continuous path will be continuing in this other, using this other map, not that one, right? So that's saying that in such a way I am covering with these two open sets, the image of these two guys are covering all the x, right? So x is something like this. It's something like this. So here you have one copy that it's, let's say here we have R1, R2, R3, R4, R5, and R6. So here we have one cut and the other cut. So it's like we are pasting these two spheres along this path, and we're producing x, right? But here this is not x, it's x with these roots removed. Well, this is the point R1 0, R2 0, R3 0, right? And also I have to remove the infinities, because the infinities do not belong to x. So here I have one infinity and the other infinity, right? So what is the homology of this thing? So the H1 of x, it will be isomorphic to set to 2 times the genus, right? Plus something here, that it will be 1 if d is even. But what happens when d is odd? When d is odd, I have to consider infinity as one of these roots. He's taking the place of one of these. So the infinity will appear here, for instance. So I'm just removing 1 point when d is odd, right? So this guy, alpha, will be 0 if d is odd, and 1 if d is even, right? And what is the genus? Who can tell me what is the genus? How can you compute the genus easily? What's the relation between the genus and D? So G is, if D is odd, it is G is what? D plus 1? Minus 1. D minus 1 over 2. And when D is even, is D over 2, right? So if you combine these two things, you will see that in fact this is always set to the D. Minus 1. Right? Is it fine? No, this is D minus 2 over 2. Right? Yeah. Here we have an example. 6, and the genus is 2, right? Okay, so this is an example where we can see actually the topology of the algebraic variety. But in general, we're not that lucky. Okay. Okay, so I'm not sure. Okay, I have time. Well, in general, well, do you have any questions about this example? No? So, well, in general, if X is a smooth, compact manifold, we know that the homology groups are finally generated abelian groups. Yeah, here these are finally generated. And so we know by this theorem of classification of finally generated abelian groups that this is isomorphic to some free abelian group of finite rank plus some torsion part, right? And the torsion part, we can always write it in this way. Right, where this d1 divides d2 and divides dr. Okay, so if we're looking for curves, we never will have something like this, right? We will never have something like this. The curves always, the homology groups of curves are always free. They have no torsion. But there are examples of algebraic varieties, even compact, even projective, where these homology groups have torsion. So this is the second example. So consider the projective variety given by the Fermat equation, the Fermat quintic surface. Okay, what does that mean? This is the variety X defined as the set of points x0, x1, x2, x3 in the complex projective space P3 with complex coefficients such that x0 to the 5 plus x1 to the 5, x2 to 5 plus x3 to 5 is equal to 0. Okay, so this is a subset of the projective space of P3, defined by exactly one equation. Oh. Sorry, no. No. It's not It's not a fivefold. It's a surface of degree 5. Okay, so everybody understands what does that mean, right? I mean, you know that the projective space is not, you cannot define functions on the projective space, right? But you can define the zero locus of homogeneous functions defined over the projective space, right? This is well defined. Okay, and this is a projective variety by definition. So it can be shown that the Fermat quintic surface is simply connected. Okay, this is not so simple, but it's simpler to prove that the H1 of this is 0. That can be proved easily. Okay, and if we consider the action, consider the group, the action of the group of G set over 5 set, and this is isomorphic to the cyclic group generated by 1/5 root of unity. It's inside a C star, right, where this guy is the exponential of 2 pi I over 5. Okay. And you consider the action in the following way. You say that this 5th root of unity acts on the point x0, x1, x2, x3 in the following way. So it fixed x0. It multiplies 1 time in x1, 2 times in x2, and 3 times in x3. Okay, so this is an action. This is a properly discontinuous action. That's easy to prove. And so we have a quotient. So we have the quotient, and the fundamental group of the quotient will be isomorphic to Z over 5Z, and since this is abelian, the first homology of this quotient is a finite group. Okay, so it has torsion, and it can be shown. That is, well, it's also difficult, but not so much. That this guy is in fact a smooth projective variety. That means that this guy is isomorphic to some subspace of some projective space, maybe of higher dimension, and a lot of equations, homogeneous polynomial equations here. Okay. What else? Do you have any questions so far? No? Okay, so I will continue. Okay, so beside these homology groups and relative homology groups, we can define in general homology groups and relative homology with coefficients in any group, any abelian group. So let's say let XA be a pair of smooth manifolds and G any group, abelian group. Then we define the relative homology. So we define the relative homology with coefficients in G. So it will be, for us, by definition, the homology of the complex Cx over Ci, but with coefficients not in zeta anymore, Now it will have coefficients in G. Okay, so this is exactly the same thing as doing the tensor product with G, and this is the same thing as taking this thing right, where this guy, let's say Cn of X tensor with G is nothing else than this set of formal sums Ni Fi I in I, where Ni now is in G, Fi is singular n simplex, and I is finite. Okay, so it's the same thing, just taking coefficients in an abelian group G. Okay, and we can also define the cohomology. So we have the cohomology groups, the relative cohomology groups with coefficients in G defined in the following way. Hk of xag is by definition the cohomology of the following complex. Now you have to take home of the complex of relative chains to G, right? With the dual of the boundary operator, right? And this is the same thing as the cohomology of the home of Cx to G divided by the home D, right? Okay, so, and you define the singular cohomology with coefficients in G as the singular cohomology, the relative singular cohomology with relative to empty, okay? And in our notation, we will always, whenever we forget G, we are referring to G equal to the integers. Okay? Okay, so finally, to finish this class, I will recall the universal coefficient theorem that relates the singular homology with integral coefficients with the singular homology with coefficients in a group and with the singular cohomology. So, theorem, this is universal coefficients. So let XA be a pair of smooth manifolds such that A is contained in X. Then, so the first theorem about homology, there exists short and split short exact sequence so this is the first part. This HK XA tensor with G to the XK XA with coefficients in G, and here we have the Tor 1 of HK minus 1 XA with coefficients in G. Oh, sorry. And the second part is about cohomology. So there exists a split a short exact sequence. Now it's with the home, so it is the x1 of hk minus 1, x relative to a and g. It goes to hk, the singular cohomology with coefficients in g, and the home of hk to g. Okay, so using these theorems, we can relate the singular homology groups with integral coefficients with the singular homology group with coefficients in a group, and the singular cohomology with coefficients in a group. So what are these x and Tor? Where Tor1 and x1 are defined in the following way. So let 0 f1 f0 m0 be a short exact sequence of abelian groups where f0 and f1 are free, and consider any abelian group n. Then the Tor1 of m and n and the x1 of m and n are the groups that make the following following sequences exact. So this can be considered as the definition of these groups. They are defined up to isomorphism. So the Tor appears when you take the tensor product. So here you will need to, whenever you take the tensor product with an abelian group of a short exact sequence, it remains exact almost everywhere except here. So what you have to add in order to get an exact sequence is the Tor1. So here you have the Tor1 of mn, and then you have the f1 tensor with n, f0 tensor with n, and m tensor with n. And with the home, it happens the opposite thing. I mean, it will remain exact here, but I know it's the same thing, but the home is contravariant, right? So you will have to add it at the other side. So you will have here the home of mn, the home of f1 n, it's f0, f1, and here you add the x1. Okay, so these are the universal coefficient theorems, and well, we will use them in order to compute things. You don't need to know exactly all the proofs and you just need to know how to work with these things. Even with the Tor and the Ext, in the course we will just use some easy properties about this. Okay, any questions? No?